Good afternoon. Today I'm finally ready to present the finished device. All the components arrived, everything has been soldered, assembled, debugged, and it's all working. In the schematic, I implemented a small modification of my own. I was curious to see how the CH1024 Power Delivery chip would work when powered from a charger. This chip negotiates the required voltage. In my case, I'll be using a Raspberry Pi power supply. For this setup, I'll use 12 volts, so we'll be drawing 12 V from that power supply. Since the power adapter does not provide galvanic isolation, I will use it for testing only. For real operation, you can use a power bank like this one. It also supports 12 V output via the power delivery interface. What else? I used a 3.5mm jack to connect the probes. The probe itself is built like this, with a 2-menar trimmer resistor. Right now, it's set to some minimal resistance. I didn't check the exact value. In addition, the schematic includes a 0.10 current sense resistor. Test pads are provided for measuring across it, as well as a test pad for monitoring the output voltage after the linear regulator. Even if the power delivery chip has power, the LDO could still fail, so this allows us to verify proper operation. If the circuit were slightly modernized, the LDO could be replaced with a 12V to 9V Amtech DC-DC converter. It comes in a compact package that would fit here without changing the PCB dimensions. Then it would be possible to use a standard 12V power supply directly. That was my initial idea, but since I already have this power bank, I decided not to implement it. In version 2.0, I'll probably build one with a DC-DC converter and galvanic isolation, just for interest. Now let's power up the board. We connect the supply, the LEDs light up. We connect the probe, the resistance drops, the capacitor discharges. Gradually increasing the resistance, we see the scale rise. Turning it back, we see the indication change accordingly. According to the technical specification, current consumption should be less than 100 mA. To measure it, we'll check the voltage drop across the 0.10 resistor. I'll set the meter to the 200 mV range. The accuracy won't be extremely high, but it's sufficient for our values. I managed to measure about 3 mV. So 3 millivolts across 0.1 ohms gives 3 mV, 0.10 or 30 mA. So the current consumption is about 30 mA. Why is it so low? For the indicator LEDs, I used 4.3 kilo resistors. That means each LED draws about 1.3 mA. The logic high level at the comparator outputs is around 7.58 V. Considering about a 2.5 V drop across a green LED, that leaves roughly 6 V across the resistor, resulting in approximately 1.3 mA per LED. So roughly 13 mA total for the LEDs, plus the rest of the circuit, which brings us to around 30 mA overall. That seems reasonable. So that's it. I hope this homework assignment will be accepted. By the way, for soldering control, I used a very convenient plugin. It's useful to give to assembly technicians. It takes the BOM file and allows them to check off each soldered component, visually confirming what has and hasn't been assembled. Overall, a very practical tool. That's all for now. Bye-bye.